Hello everyone, this video is the first part of machine learning in practice using Python, specifically using the library Scikit-learn. Scikit-learn is a machine learning library in Python that is built on top of numerical Python, scientific Python, and matplotlib. The library is actually simple and efficient for conducting predictive and other types of data analysis related to classification, regression, clustering, and dimensionality reduction. Besides to these supervised and unsupervised learning algorithms or models, the library has also some methods and functions that could facilitate model selection and data pre-processing. So for further details about this package, you can go to this Scikit-learn documentation and you can explore how it works for each of the different types of problems. So in this tutorial we are going to use this Scikit-learn library specifically for modeling supervised learning algorithms. In the supervised learning algorithm, we have a data set given with labels. So the objective is to approximate the unknown function f that maps the input space x to the output space y. Or we are interested in estimating the model y equals f of x plus an inner term e. And this function f actually represents the true relationship between the inputs x and the output y, but this function is unknown. So coming to that of the ordinary least squares regression, as you know, regression predicts a continuous or in general a quantitative response variable y based on a set of input features, let's say x1, x2, xp. In general, in machine learning, the target function here y equals f of x plus e is unknown. So the functional form of this model is not specified, but specific to a linear regression problem. This target function is simplified to a linear combination of the covariates. So it can be written as y equals w naught plus w1 x1 plus w2 x2 plus wp xp plus the error term e, and can be written in summation notation in this form and in matrix notation in this form. So here w naught is the bias or the intercept or constant term of this model, and wj is the weight associated with the j's input feature xj. So here the goal is to find the values of the parameters w naught and wj's so that the sum square of error is minimum. So the sum square of error is the function of the parameters, which is the sum of the square of the deviation of the actual value of the target or output variable from its corresponding fitted or predicted value. So we are interested in finding the value of the parameters so that this sum square of error is minimum. So in this tutorial we are going to look at specifically importing the data that we are going to use to fit the OLS regression model, and then examine our data. And there is also a need to separate input and output features into different data frames. So we'll look at this one also, and after that there is also a need to split the data set into train and test sets for two different purposes. Specifically, the train set is used for training the model of interest, and the test set is used for measuring the performance of the model for unseen data or data set that is not used for training. Then after that we'll see how to train the model and evaluate the performance of the model, and lastly we'll see how to validate the trained model using a method called cross-validation. So the data that we are going to use is actually called the Boston housing dataset. This dataset was part of the scikit-learn library in the earlier versions of the library, but due to some sensitive variables related to proportion of black residents and a variable indicating lower socioeconomic status, this data has removed from the current and latest versions of scikit-learn. But for us, for this tutorial, we are going to rely on this dataset importing from a certain local repository. So this dataset has some variables related to crime rates, residential land, non-retail business, and whether the house is related to Charles River or not, nitric oxide concentration, number of rooms, and so on. And finally, our target or outcome variable is the median price of the house. So we are going to model this price on all the other variables, considering them as covariates. Now for this purpose, we are going to rely on the scikit-learn library. So let's upgrade this scikit-learn library in order to use the latest version of the library. So for this, we use pip install -- upgrade scikit-learn. So running this cell will upgrade the scikit-learn library to the latest or the current version. Now it's upgraded, so let's see the version that is currently installed. So now we are on scikit-learn library version 1.7.1. We need also the numerical Python and pandas libraries, so let's import them. Here we have this 3 line of codes. They do not have any significant impact, but just let's simply run them. Now let's import the data that we are going to use, which is the Boston housing dataset, from my GitHub repo. So let me run it. So this displays the first 5 observations of the data. We call this data, let's say, housing underscore df. So here we have the variable crime, zn, index, chas, nox, and finally here we have the median price of the house as price. So we are going to model price on all the other variables. And first we have to examine this data before directly going to fit our model of interest. So housing df is the data that we have imported. So by adding this method shape, we can determine the number of rows and the number of columns of the data frame. So this indicates there are 506 observations and 14 variables. It is also essential to check for missing values. So for that purpose, on our data frame name housing df, we need to call the method isNA. So this gives you the results something like false, 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 and so on. So here this isNA method checks whether each value for each variable is null or not. So false stands for it is not null, and true stands for it is null. But it may not be clear from this data frame indicating something like false, 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 and so on. So here false is a boolean value representing 1. If there is any true, that true value represents 1. So for example, if we add all the values for crime, if the value becomes 0, that means there is no null value. Otherwise, if the value becomes something different from 0, that means the crying variable will have some missing values. So instead of examining or checking whether each value for each variable is null or not, it is better to add the values of this Boolean variable. It's essential to add these values, right? So if the values are 0, there is no null variable. Otherwise, there could be some null values. So for that, under is and a method, we need to call the other method, let's say sum. Then this adds these values for each variable. So running this, now it says for each variable it becomes 0. That means each variable has no missing observation. In practice, there could be several missing observations. So in that case, there is a need of just considering missing value imputation techniques. And we can also describe the data types associated with our data frame using the info method. So it lists the variables and it lists also the number of null values, and here we have the data type. And actually this doesn't have that much significant or important information. And we can also obtain descriptive statistics for each variable that are included in the dataset using the describe method. So running this cell gives these descriptive statistics. For example, the count or number of observations of each variable, the mean, standard deviation, minimum, the first quartile or 25th percentile, the median or the second quartile or the 50th percentile, the third quartile or the 75th percentile, and also the maximum value. So these are the descriptive statistics associated with each variable that are included in the dataset. And if we are interested, we can also examine the correlation among the variables using the method core. So if I run this cell, the correlation matrix will be this one. So for example, our main target variable is price or outcome variable. So for crime, it becomes minus 0.39. So a larger crime rate tends to decrease the price of the house. And the other, for example, if we consider this chas variable, this chas variable is actually a binary or dummy variable indicating whether the house is near to the Charles River or not. So the correlation is something like 0.14. So since it is binary, that means a house near to the Charles River is more likely to have higher price than those houses which are not near to that river. And if we consider the environmental pollution NOx, here it is negative. That means when the NOx concentration is higher, the price tends to decrease. So you can look at all the other variables in the we can look at all the other values in the same way. Now there is, once we have imported the data, there is a need to differentiate the input and output features data into different data frames. So for example, let's here in our data frame prices are dependent or target variable. So let's separate this from the rest of the variables, and all the other variables are going to be considered as covariates. So again, we need to present these variables in a separate data frame. So for this purpose, housing df is our data frame that we have imported. So let's drop the column price because price is our target variable. Then let's associate this data frame consisting of all the variables except price into XDF. So XDF has now 506 rows and 13 columns. That means there are 506 observations and 13 columns or 13 covariates. Similarly, for the target variable, we can simply extract the price variable. Housing df in square bracket and under single or double quotation, we can use price. Since we have only one variable, let's say just use the method values in order to display the values instead of considering it as a data frame. So now this is the values of our target variable or dependent variable. Now we have split the data into input features data frame and results of output feature. Then next we need to split the data sets, that is both the input features dataset and the output feature dataset into train and test splits. So the train set is used for training the model of interest. That means it is used for evaluating the model's approximation to the target function, and the test set is used for assessing the performance of the model for its generalization ability or its performance for unseen datasets that is not used for training. So the entire dataset, which is the input features dataset and output features, should split into train set and test set. And here we have another split. We'll come to this point later, but for now we need to split into train and test. So to split the dataset into train and test, we need to call the that's of the module train test split. This is obtained from that of scalar dots model selection. So I need to execute this. Now the train test split module is imported. Then we can use train test splits. This one, train test splits, input features data frame, output features, then the train test split ratio. This is the test size 0.30. That means 30% of the observations will be considered as test set and the remaining 70% will be considered as train set. And for ease of reproducibility, let's use the random state 42. So this will return 4 values. The first value will be the train dataset of that of the input features, and the second the test dataset of the input features, and the third the train data of that of the target variable, and the fourth one the test data of that of the target variable. So let me execute this cell. Now the train test split is done. So let us see that's of the train input features data. Now these are the train input features data. Here look, we have 5, 116, 45, 16, 468 and so on. So these are the indices or observations selected for that of the train set, and all the other correspond to that of the test set. And similarly for that of the train outcome data, we can call yTrain. So these are the data or observations of that of the train outcome variable. So simply we can examine the train input features data frame and the test input features data frame shapes for ease of just comparability. Here the train input features data frame has 354 observations and 13 variables, but the test input features data frame has 152 observations and 13 variables. So both the train and test input features data frame have the same number of variables, and it must be. But in terms of number of observation, 70% of the observations of the original data frame belong to the train set and 30% belong to the test set. Similarly, for the target variable, there are 354 observations of the train target variable and 152 observations of the test target variable. So X test has 152 observations and the target variable has also 152. X train has 354 observations, Y train has also 354. So here X train df and Y train are going to be used for training the model, and X test df and Y test are going to be used for evaluating the performance of the model for unseen data or dataset that is not used for training. So now we split the data into train and test. Now we can fit or train our model of interest. We are interested in the linear regression model, particularly on the ordinary least squares model. So we need to import the module linear regression from sklearn.linear model. So let me run this cell. Now the module is successfully imported. Now we need to call this model linear regression and assign, let's say, certain object name OLS-reg, and then let's call just OLS-reg, and let me run this one. Now this produces this output, right? Now this is just simply a container that is used to train the model of interest, specifically the linear regression model. So here, for example, if we click on the parameters, it has some parameters like fit intercept true, copy x true, tolerance 1 times e to the power of minus 0.6, and so on. So here, for example, if we point to the symbol something like I, it says not fitted. Therefore, this is just a container used to store the model that we are going to fit or train. So currently, the model is not trained. It's just simply a certain container or initialization. Now, if you want to look at more about how this, let's say, module works, you can click on here on the symbol that has something like a question mark. If you click on that, it opens that of the linear regression documentation. So here, sklearn linear model dot linear regression. So here you have the parameters that could be specified, and the description of each parameter is presented here. But for now, these parameters have not that much meaningful value, let's pass. But if you are interested, you can explore that one. Now we have already initialized our model here, linear regression, and assigned to this object name OLS-reg. Now to fit the model, we need to call the method fit on our container OLS-reg, and then we have to give the training inputs data frame and the training outputs data. Then we can run this model. Now this is something like colored something like, let's say, orange. Now the color for the trained model becomes something like blue, right? If we point to the symbol something like I, it says fitted. Now we have fitted or trained our model of interest. Similarly, if you click on these parameters, symbol shows the same parameters that are set. Now the model is trained, so we can extract that's of the bias and weights of that's of the model. So to extract that's of the bias of the trained model, you can use the method intercept underscore under our model, which is named OLS reg. So this will give us, now this is just an NumPy float object, the value is 31.63. Similarly, for the weights parameters, we will use the method cof underscore. And if I run this, these are the coefficients associated with each of the covariates or each of the input features. So if we look at the columns of the data frame, for example, this one is the coefficient for crime. The coefficient is negative, it's for crime. Therefore, as the crime increases, the price tends to decrease. For Zn, it is positive, right? And for that of, let's say, chance variable, which is the fourth one, 1, 2, 3, 4. Therefore, a house near to the Charles River is more likely to have higher price, right? So we have trained our model. Now let's assess the performance of the model on both the train and test sets. So first let's consider that of the training performance. When we say the training performance, we are going to assess the performance of the model using that of the train dataset. And this performance or the error is called in-sample error or training error. Specifically, let's consider that of the mean square of error. This mean square of error is nothing but the sum square of error divided by the number of observations. So when we consider that of the training dataset, n is number of observations of the trained dataset. When you consider the test dataset, n is going to be the number of observations in the test dataset. So for that purpose, for example, to determine this mean square of error or sum square of error, we need to first obtain the predicted values of the outcome variable. So for that, for the training dataset, let's say OLS, then we need to call the method predict, and as an input we need to give the value of that of what's the training input features data frame xtrain df. Then this will give us the predicted values for the training dataset. So these are the predicted values for the training dataset. And we have already ytrain, which are the actual or the true values of the outcome variable or target variable. We have obtained here above the predicted values of the outcome variable for the training dataset. Therefore, we can obtain the training errors, just ytrain pred minus ytrain. So this is just, these are the residuals or errors of the training dataset. So now the training mean square error is nothing but the sum square of these errors, divided by the number of observations of the trained dataset. So sum of train errors, we need to square each error. Sum square of the training errors divided by length of the training errors, which indicates number of observations of the training dataset. So this gives 22.54. So the mean square of error is 22.54, or these parameters, this intercept and this coefficient parameters or parameter estimates yield that of this minimum mean square error. We need a model to have the minimum mean square error or minimum sum square of error. And instead of calculating, let's say, the training errors manually, we can use also the mean squared error function from a scalar matrix. So if I run this, now this function is imported, then we can obtain the training mean square error simply by calling the function mean square error. Then we need to give the actual value of the target variable and the predicted value of the target variable. Then this will provide the training mean square error. So this is again 22.54. 22.54 here also. So the ones that we have calculated using the manual procedure and the one using the mean square error are exactly the same, almost exactly the same. But we need a model to have a minimum mean square error. But how small is this? It's just subjective, right? The mean square error is non-negative, but is it small or large? It is really difficult because the judgment would be subjective. But instead, the default performance metric in scikit-learn is the R-square measure, or which is called in statistics coefficient of determination. Now this coefficient of determination or R-square measure is a normalized version of the mean square error, which is defined as 1 minus that of the unexplained variation divided by the total variability. So if the R-square is close to 1, the model has good performance, but if it is far from 1, the model has just, let's say, a poor performance. So this R-square measure doesn't depend on the scale of the data, or let's say the actual observed values of the data. And compared to that of the mean square error, this is easily interpretable. So instead of relying with that of the mean square of error, it is better to rely on that of the R-square measure, which is more interpretable. So to obtain the R-square measure or the coefficient of determination, we need to call the method score, and we need to give just the input features data and the output features data. So OLS-reg is the our model that we have fitted before, so we need to call just the method this one, and we need to input this input features data and output features data. Then finally this will return that of the R-square measure. So it becomes 0.74. Now here we use the training data, therefore this is the performance of the model on the training dataset. So 74% of the variation in the median price of the houses is explained by those covariates that are included in the model, but the remaining 26% is explained by other variables that are not included in the model. So this is just the performance of the model for the training dataset. But in machine learning, we are not only interested on the performance of the model on the training dataset. Rather, we mainly focus on the performance of the model for unseen dataset or dataset that is not used for training. So for that, we need to consider what we call the out of sample performance or test performance. So we have already trained our model OLS-reg. Then we need to use the method predict, and then we can provide x-test df. Therefore, this will be the predicted values for the test datasets. Let's name it as y-test pred. Then after that, to obtain the test mean square error, we can call the function mean square error, and then we have to input the actual value of the target variable of the test set and the predicted value of the target variable for the test set. Then this will provide the test mean square error. Now the test mean square error is 21.52, and here the train mean square error is 22.55, let's say. So as said before, instead of considering this mean square error, it is better to consider the normalized version of this mean squared error. So it's better to consider that of the R square measure. So for the R square measure, as we have seen before here, while let's reg dot score, we provide the training data sets of input features and the output feature. So here we need to provide the input features of the test data frame and the output features of the test data. So if I run this cell, this becomes 0.71. Now the model performance on the training data is 74%, and the model performance on the test data is about 71%. So we can say that here the model performs better in both the training and testing set. But here we used a single train test split, right? So the this performance may be by chance. So instead of relying on a single train test split, it is better to use what we call k-fold cross validation. That means the data is going to be split into k different folds, and under each fold we need to train a different model, considering each split as a test set and all the other splits as a train sets. So for that we are going to consider this cross validation, or what we call k-fold cross validation. So the idea is to split the data into, let's say, 5 or 10 different folds. Let's say we are going to split into 5 folds: fold 1, fold 2, fold 3, fold 4, and fold 5. And here each of the fold has 5 splits. So one of the splits, for example for fold 1, the split 5 will be considered as a test data set, and all the other 4 will be considered as a train data set. So we could obtain the in-sample error performance and the out of sample error performance, or the training error and that's of the test error. For fold 2, we may consider, let's say, split 4 as a test data set and all the other splits as a train data set. Then again here we could obtain the train error or train performance and test error or test performance. And the same is true for fold 3, for fold 4, and for fold 5. Then once we obtain this training error and testing errors, or training performance and testing performances, next we need to average this in sample and out of sample performance. So the average score will be considered as the cross validation score. So if the cross validation score is less than the score using that of the full training set, in that case the model is something like overfitting the data. But if the cross validation score is greater than that of the model fitted on the full training set, the model is underfitting the data. But if the cross validation score is approximately the same with that of the model fitted on the full training data set, so the model is better. It is neither overfitting nor underfitting. So here, if the cross validation score is less than the one that is trained on the full training set, the model is overfitting. That means the model memorizes the training data set. Yeah, the model memorizes the training data set, but its performance for the test data set will be poor. And when the cross validation score is greater than that of the model trained on the full training set, in that case the model is underfitting. That means the model couldn't capture the underlying patterns of the training data set. So we don't need a model to be an overfitting and an underfitting. Rather, we need to have a model that balances these overfitting and underfitting problems. So the model should learn the main patterns or underlying patterns of the training datasets, and at the same time the model should have a good performance for the test dataset. So here for this single train test split, the train score is 74%, the test score is 71%. It is good, but it could be by chance. So to check this, we need to validate the model using this cross validation. So for cross validation, we need to import this function from a scalar model selection. So I can import this function cross val score. Then now to use this cross validation score, first we need to initialize our model. OLS reg equals linear regression. Now here we are initializing our model. Then this initialized model is going to be supplied as an input for this cross validation function. Cross val score OLS reg, which is this initialized model, then the training data frame of the input features and the training outcome values or the training outcome data. And here CV is nothing but number of cross validations or number of folds to be considered. Let's say 10. Therefore we are going to have 10 different folds, and in each fold we are going to train the model on 9 of the splits and test the model on only one of the splits. So here we could obtain 10 different scores. That means 10 different R squares. So let me run this. Now the R square scores for these 10 folds are here. For the first fold is 70, let's say 71%. For the second, 76.6%. For the third, it becomes 22.5%. For the fourth, 79.7%, and so on. Therefore here we have 10 different folds. The performance for each fold is different. So the performance of the model will be the average of these different scores. So the mean R square using this cross validation is, we can obtain np.mean CV scores. This one, average of this cross validation scores or R square scores. So let's obtain the average. Now the average is 0.6875. It's about 68.75%. This is the cross validation score. Previously we obtained already the train R square. So let me run this. It was 74%. The train R square is 74%, but here the cross validation R square is around 68.8%. So here the train R square is somewhat larger than that of the cross validation R square, and specifically if we find the difference, train R square minus, let's say, this cross validation R score, and it becomes something like 5%. Usually, to judge whether the model is neither overfitting nor underfitting, it is recommended to have a difference less than 2%. Now this becomes 0.055. It is around 6%. So this may indicate something like an overfitting. The model has something like an overfitting problem. So actually the performance of linear models depends on the degrees of freedom or the number of input features. So if the number of input features increases relative to the number of observations, then regularized methods or penalized regression models may perform better. So in the next video we'll concentrate on these regularized regression models, which are called regression, lasso regression, and that's of elastic net regression. So this is all about today's video. Thank you.